We discussed in this video about non-regular languages. Obviously the same as non-recognizable languages. And we spent a lot of time to discuss about different types of recognizable languages, and we discussed about automata and regular expressions and different types of closure operations, building more and more regular or recognizable languages. But the point is that there are many languages that are in fact not regular, not recognizable. And I would like to discuss in this lecture essentially one example and one tool to prove that a language is not regular. The example is the language formed, so this is a binary language over alphabet A and B, and it's formed by these types of words, A to power n, B to power n, for n greater than or equal to 0. And I'm saying this is not regular or recognizable. And I'm going to prove this for you in the following way. Let's assume that this was recognizable. And it was recognizable by some automaton A consisting, and I can choose this obviously to be a deterministic automaton. And this is made of this input alphabet, and sigma is just AB. This is the transition function. We have the initial state and F. And let's assume that the number of states we have is some number M. And I would like to consider the word A to power M, where with M exactly the number of states in Q, B to power M. And this is obviously a language from L, so it means that there is a successful computation, an accepting computation on this word. So delta of Q0 and A to power M, B to power M, this leads to a final state. And I would like to show this computation. So we start from state Q0, and we are going to read first these M's. So this is the first A I'm reading, and that takes me to a state Q1, and then I'm reading the second A, and that takes me to some state Q2, and so on. It takes me, the last one is going to take me to a state QM. And then I have with letter B, it takes me to QM plus 1, and then I read the second B, and this is QM plus 2. And so on, the last B is going to take me to state Q2M, and that has to be a final state. And so here is the crucial point. Remember that M is the number of states in your automaton Q. You only have M states. But if you look at this, we have, in fact, here, in this part of the computation, we have M plus 1 states. So the point is that because you have M plus 1 states and you have only M states available, it means that there really has to be, so there is I and J in such a way that Qi is equal to Qj. So in other words, you have got to use the same state twice. Because you really need M plus 1 states in here, and you only have M states. So there has got to be a repetition of states. And so in that sense, the way this computation looks now is in fact like this. You start from Q0 and you read some A's, and you go all the way to Qi. And then you continue reading, and you go to Qi plus 1, and so on, and all of a sudden you get to Qj minus 1, and in fact this will bring you to Qj, which is in fact exactly the same as Qi. And you read this, and at some point, one of these, as you cycle through, you are going to get to this Qm, which is one of the states here. And that will then continue the computation to, Qm plus 1 and the rest of these things going to Q2m. And the point is now that we have this cycle in here. So what this means is that if I just think about this computation so I can also have this computation. So I go from Q0 to Q1, and I go to Qi, and remember this Qi is the same as Qj. And so with letter A, I can go now to Qj plus 1, because from Qj to Qj plus 1, this was there was a transition. And I can continue from here, to Qj plus 2, and so on to Qm, and then with B transitions, all the way to Q2m. And so if I think about this computation where I just, cut these parts of the A's. So how many A's do I have? B's is clear. I mean, I have the same amount of B's as I had before. But number of A's now, I have, so I'm just going to somehow calculate. I will have as many as I had before, minus J minus I, which is what I eliminated by really observing that Qi is equal to Qj. So what this gives me is that the amount of B's is the same as before, so B to power m, but here I have A to power m minus J minus A. I have just eliminated these, and I still have a successful computation. So this has got to be, so maybe I'm just writing it like this. I have a successful computation, an accepting computation from Q0 with this word. This will bring me to a final state just by following this computation I wrote on the previous whiteboard. So this implies that A to power m minus J minus I B to power m is in your language, and this is a contradiction. And it's a contradiction because really you were supposed in this language to have these exponents equal, and obviously these exponents are not equal. So that's a contradiction. And in fact, this basic argument that I have used in the proof of this example can be generalized. And this is a celebrated result. It's called pumping lemma. And I comment in just a moment what makes it pumping, what's the pumping part of this lemma. And what this says, the pumping lemma is like this. For any regular language, or recognizable if you like, there is an integer, so there is n greater than or equal to 0, such that, so if I say for any language L, such that all words in L longer than n have a decomposition. So all words U, if you like, have a decomposition U equals, let me just modify the notation just so that I can follow my my notes more carefully. So this is a word X, and the decomposition is X equals to U V W with the following properties. So there is a decomposition with the following properties. And we have on one hand the length of UV is at most n. And the other one is the length of v is at least 1. And u to power v, u times v to power I times w is in your language for all I greater than or equal to 0. And I'm going to prove this for you. I just comment on this result a little bit more. So this is a great tool that you have to prove that some language is not regular. And the way this is going to go is that you are going to assume that that example you have in front of you is in fact regular. And this tool is going to allow you to choose a word, any word you like of length sufficiently large. And once you pick a word from that language, you will have as a consequence that many other words have to be in the language. You essentially will have a part of that word that you can pump. Pump meaning you can insert many copies of that part of the word. And when you do that, you will stay in the language. And that's going to be a great tool for you because depending on how you choose your word, you might come to the conclusion that not all of these words can be in your language, and that's going to be a tool to show that that language is not regular. So the pumping part of the lemma comes from this result, from this part of the composition. This part V, you can pump, you can put lots of copies of V, and that's going to still stay in the language if your language was regular to start with. So here is how we prove this result. So the proof is exactly the same as we had in our example. So L is recognizable, so that means that it's recognized by some automaton of the form Q, sigma, delta, Q0, and F. And let's just denote the size of Q, so the number of states you have with N. And let's take an arbitrary word. X from L with length greater than N. And because it's in the language L, then I will have a successful computation on X. And if I just denote the letters of X, so they will be A1, A2, all the way to AN plus 1. So if I take this computation, so with letter A1 takes me to Q1, and with letter A2 takes me to Q2, and so on, with letter A. In fact, you know what, this is enough if I take it up to, so from N, and it's going to be enough for my argument. So with the last letter AN, that will take me to state QN. And the point is, just like before, the point is to observe that in this successful computation, you will have N plus 1 states. And that really implies that you will have at least one repetition of states in this computation. And remember, this is a successful computation, so this is it leads you to a state in F. So the moment you realize you have a repetition of states, so what this means is really that there is, so you will have I and J, so there is something like this, I smaller than J smaller than N, such that Qi equals Qj. And you can also just choose the first occurrence of such a pair. So you choose the smallest such J. So it's really going to be the first time you have a repetition of states. And by having the smallest, so that means that really, let me just write it like, so you will choose smallest / j, and the way this is going to go is going to be q goes to q1, and it goes to qi, and it goes later on to qj, and these are in fact the same state, and then it continues to qj plus 1, and so on. And obviously, I mean, with the appropriate letters. And I'm just going to denote this part of the word. So U, this is going to be A1 all the way to AI. And this part of your word X is going to be AI plus 1 all the way to AJ. And because I have A smaller than J, V is obviously not the empty word. And this part of the word is going to be W, is the rest of my word. It's AJ plus 1 and all the way to AN. And because I'm choosing the smallest / j, it's the first time I see a repetition, so the length of UV is really smaller than n. Otherwise, I could find earlier times some repetition. So I already have my decomposition. My input word is now decomposed in the form UVW, and I do have the first condition, I do have the second condition, and now the point to observe is that really this is a cycle in here. So for example, I could skip over this cycle, meaning I don't have to calculate the word V. So from QI, I could jump all the way to QJ plus 1, because really QI and QJ is exactly the same. So let me make this point to you here. So my computation now looks like this. From Q0, I go with U in a number of steps to QI. And then with a number of steps, I go with word V to QJ, but QJ is equal to QI. And then with the rest of the word, I go to QN, which is a final state. So that's how my successful computation goes. And so just by observing this, you can now see that in fact UV to power K W is in your language for all K. And simply that's because you can have a successful computation of such a word simply by going with U here, and then taking this cycle enough many times. You take this cycle K times, whatever your K might be, 0 or more, and then at the end you continue this part of the computation with W. So that's always going to bring you to a final state. So that's the proof of our result, and it's really a powerful result. We are going to use this in proving in the demo sessions that a number of results, a number of languages are not recognizable. But here is just one more example. This is also going to help you in your demo sessions. And here is, now I'm combining the tools I have given in this video lecture with some of the other tools that you have seen in some of the previous lectures, meaning I can also take intersection, or I can take the complement sometimes, but in this case I'm going to use intersection. So my example is going to be that this particular word K, which is a word over A and B, where the number of A's is exactly equal to number of B's. And I'm saying that this is not regular. And here is the proof. You will have several other examples, and you will have to be creative in choosing your tools, how to show in your demo sessions how these languages are not regular. But here is how I'm choosing my tool in this particular example. You always assume that, assume the K is regular. And here is the creative part. You could go about this in different ways, but I find that one easy way is also to realize that that this implies that K intersected with the language of this regular expression, A star, B star. That also has to be regular or recognizable, right? Because this is a regular language, and I have just assumed that this is regular, and the intersection of two regular languages is regular. But now we have to think about this. So this intersection, I mean, what language is this? So obviously, these are words of the type, maybe I'm just writing. So because it's A star, B star, it's got to be A to power M, B to power N. So a number of A's followed by the number of B's. But also it's got to be in K. So the number of A's and B's has to be equal. So it's with this property, M has to be equal to N. And obviously that's exactly the language A to power N, B to power N, with N greater than or equal to 0. And that's a contradiction, because we just proved, in this lecture that this language, in fact, is not regular. So because I have this contradiction, then my assumption doesn't hold. So that implies that K is not regular. And so very often you will have things like this. You can have a direct proof that the language is not regular using something like the pumping lemma. Or you can have an indirect proof. Just assume that the language is regular, and then by doing some sort of clever construction, such as this intersection, you will conclude that some other language is regular, and for that one you have direct evidence that it's not regular. So we will check more examples of this type in the demo sessions.